Okay, so in the last class we saw the calibration blocks, and we learned how these blocks are given a particular number, and from that number you could not only identify the block, but you could also get the dimensions of the block and also the flat bottom hole that you have to calibrate the instrument. Okay. So, in this class today we will see how these blocks are used to do the calibration. Okay. So, we will first take up the distance amplitude calibration, and then we will go on to see the area amplitude calibration. Okay. So, first let us start with distance amplitude calibration. So, for this what you need to do, first you need to select a particular block number, and in case of distance calibration, that block is number 5 block, which is this one. Okay. So, the first step is take this block, okay. So, what is this block? Now, you can easily identify what kind of block is this. This is having a flat bottom hole, the diameter of which is 5 by 64th of an inch or 2 mm, okay. And the metal distance in this case, as you could see from these 4 numbers, is 3 inches or 75 mm. Okay. So, you have a 2 mm diameter hole and 75 mm of metal distance in the first block that you have selected in order to calibrate the distance. Okay. So, now what we are going to do, we are going to keep this hole size constant, okay, and then vary this metal distance by selecting other blocks and collect a number of data points in terms of the distance. Okay. So, we will collect the intensity of the echoes coming out from these flat bottom holes as a function of metal distance. Okay. So, with that data we can plot a curve which can be used for calibrating the distance. So, take that block, this number 5 block, and do this. Now, take the ultrasonic probe and move the probe over the block horizontally. So, from one side of the diameter to the other side horizontally you move it till you get a maximum signal from the flat bottom hole. Okay. So, you have to move it because you need to get the maximum signal out of this flat bottom hole. That means your ultrasonic transducer probe should be right above the hole, so that you get a maximum signal. Okay. And once you get that maximum signal, you need to adjust it to 1/4 of the maximum height, and that you can do by adjusting the gain control that you have in the instrument. So, bring down this maximum signal to 1/4. Okay. 1/4 of the maximum attainable height or metal or attainable intensity that you have. So, you need to do it by using this gain. So, that means at this point in time I should also tell you what do you mean by gain and how you control it. Okay. Gain, as the name suggests, you may all know, this is to increase or decrease a particular intensity or an amplitude of a signal. Okay. So, in this case the gain is about increasing or decreasing a sound wave signal, and it is defined in this case as (20 log A2 by A1). That means A1 is the initial amplitude, and if you increase it to A2, so the ratio, the log of this ratio multiplied by 20 is the gain. In sound waves, it will be in terms of decibel. For example, if you increase the amplitude twice, okay, then gain will be (20 into log 2) or 6 decibel. Okay. So, this is how gain is defined, and there will be a knob on the instrument. So, through that turning that knob, you can adjust the gain, you can either increase or decrease it. Okay. So, in this case we need to decrease it by adjusting the gain, so that the maximum height of the echo that you got from the flat bottom hole, that should be brought down to 1/4 of the maximum height. Okay. So, that is how you set the control first, the gain control, and now once you set this gain control and make it 1/4 of the maximum height, you use the other blocks, the other metal distances that you have, and after that for the other blocks you do not touch this gain control. Okay. So, the gain control is set only once in the beginning for the first block, and when you obtain the echoes from the other blocks, okay, in those cases you simply need to note down the height of the echo which is coming from the flat bottom hole without adjusting the gain control. Okay. So, that is the next step. You take the other blocks, but in this case also you need to get a maximum signal from the flat bottom hole. And once you get the maximum, simply note the height of the peak without adjusting the gain control. Okay. Yeah, so that is a next step. Read the heights of the peaks after getting the maximum signal from the hole for each of the other blocks without touching the gain control. So, once you collect the data or the intensity or height of the peaks of the echoes coming out from the flat bottom hole as a function of the distance, then you can take this data and draw a plot. Okay. So, that plot will look like this. So, this height or intensity of the peaks or the echo from the flat bottom hole that is plotted, as a function of distance. Okay. Then you will get a curve like this if you plot this, which will look like this. Okay. But any intensity with respect to distance goes by this particular relationship. That means the intensity is inversely proportional to the square of the distance. Okay. So, if I be the intensity and L be the distance, so this will be the relationship. But in this case you could see first it is increasing, then going to a peak, and after that only it is decreasing. Okay. So, up to this point it is not really following this particular relationship, only beyond this point it is following that relationship and decreasing. Okay. So, that means along this line you have two different regions which are behaving differently with respect to the intensity as a function of distance. Okay. So, can you guess what these two regions could be from what we have discussed so far, particularly in the nature of the beam which is used to do ultrasonic testing? So, let me explain to you. So, if you remember in the ultrasonic beam we have seen this, the shape of the beam is something like this, and then close to the probe we have seen that there are a lot of fluctuations, and this particular region is known as near field and the other one is far field. Okay. So, in the near field there are a lot of fluctuations. So, even after transmitting the probe will still vibrate for some time. Okay. And by that time if any echo comes back to it, it will not be able to receive, because any transducer when it is transmitting cannot receive. Okay. So, for the probe to receive the echoes, these all the vibrations that you have should die down completely. Okay. So, that means in the near field if the echo is coming from a very small distance from the probe, then the probe will find it difficult to receive that echo. Okay. On the other hand, if the echo is coming from a larger distance within the near field, then the receiving will be better and the signal intensity will be higher. Okay. Signal intensity which is being received by the probe within the near field, then in that case will increase as the distance is increased within the near field. Okay. So, that means in this case this region that you have where you see that the intensity is increasing with increasing distance is the near field, because as I told, in the near field if you increase the distance the receiving is better, because the probe will have longer time for all these fluctuations to come down and then it will be ready to receive. Okay. So, as you increase the distance in the near field, the receiving would be better and the signal intensity would be higher. Okay. So, that is exactly you see in this distance amplitude curve. Okay. And that means the other side that you have, the other region that you have, that is the far field, wherein it will follow this particular relationship, because in the far field there is no question of any fluctuation. So, when you are in the far field, the signal intensity of the echoes will decrease as the distance is increased. Okay. So, that is why the curve, the DSC curve or the distance amplitude correction curve looks like this. It first increases as a function of distance, then it decreases. Okay. So, this was about distance amplitude calibration or distance amplitude correction. Now, let us go ahead and see how the area calibration is done. Okay. So, we could use the same blocks, but for calibrating the area, as I would have said before also, you need to keep the metal distance fixed and you have to vary the size of the hole or the area of the hole. Okay. So, let us see how the area calibration is done. So, in case of blocks which are used for calibrating the area, only a single number is given like 1, 2, 3, 4, 5 and so on. Okay. This is according to the size of the hole that you have, because in this case, as I said, you need to vary the size of the area of the hole, and the numbers are given in such a manner that the area of the hole is proportional to this, the square of the number. Okay. So, for example, if you have selected a number 5 hole, then the relative area will be 25. Okay. So, this is how you can collect the data or collect the signal intensities from this hole as a function of the area by simply providing the square of this number as the area. Actually, these numbers are given in accordance with the diameter of the holes in terms of 1/64th of an inch. For example, if the number is 1, then you know the diameter would be 1/64th inch or 0.4 mm. Similarly, 2 will be 2/64th inch or 0.8 mm and so on. Okay, so, now you can easily correlate why the area of the hole is proportional to the square of the number. Okay. So, in this case what you do, like what we have done for calibrating the distance, you first select a particular block. So, in case of area calibration, the number 5 block is first taken. So, that is your first data point, and as I said, this for this block the area of the hole would be 25, because as I said the area is proportional to the square of the number. So, take this number 5 block, move the probe and get a maximum signal. From the hole. Okay. Once you get the maximum signal, adjust the gain control, and make it 1/3 in this case of the maximum height of the echo. Okay. So, in case of distance calibration, we saw it was adjustment was done up to 1/4 of the maximum height, and in this case we do it up to 1/3 of the maximum height. And next, like what we have done before also, take the other blocks, and get a maximum signal for each of them, and then next is read the height of the echo for all other blocks. The echo from the hole without adjusting the gain. Okay. So, this is how you collect the data. Okay. You first take a particular block, which is number 5 in this case, get a maximum signal, then adjust the gain control, make it 1/3, and for rest of the blocks you simply get the maximum signal from the flat bottom hole and note down the height of the echoes. Okay. So, this is how you get the data, the intensity of the echo as a function of area of the holes. So, now you need to plot it. So, plot the heights. So, in this case we can plot in terms of percent of maximum indication height. As a function of relative area. Relative area because the area is proportional to the square of the number. Relative area unit. Then the curve, the plot will look like this. Okay. So, in this case the first data point, if you remember, was for 1/3, that is around 33%. So, let us say this is 20 and this is 30. So, it was, and it was for a number 5 block. So, this relative area is proportional to the square of the number. So, that means the first point was 25 and 33. So, it was somewhere around here. Okay. So, this is your first data point, which is 25, 33, because we have plotted in terms of percentage in the y axis. So, that is 33% in this case, or 1/3, and x axis is the relative area, which is the square of the number of the block. So, this was for number 5 block, which means it is 25. Okay. So, first what you do, you draw a curve or draw a straight line through this point and the origin. Okay. So, since your reference point or the point with respect to which you are standardizing the whole thing is this particular point is therefore known as point of standardization. Okay. And then you see rest of the points how they are, where they are falling, whether they are falling on this curve or if there is any, if you note any deviation, if there is any deviation, you simply have to note that deviation for a particular hole size, and when you do the test, this is the correction that you need to provide, okay, for that particular size. One thing you should remember here, you are getting some idea about the size of the defect, because that is what the idea is in this case. Okay. You have calibrated the area by using these holes, and now while you are doing the actual test, if you get a signal whose intensity is matching to the intensity of any of the holes, then you could say that the size of that flaw is close to the size of that particular hole. Okay. But one thing you should remember, this flat bottom holes that we have introduced by precisely drilling, okay, is an ideal reflector. But the actual flaws are not ideal reflector. Okay. So, what does that mean? That means the idea of the size that you are estimating from this particular curve, okay, is the lower limit of the size of the flaw. Okay. So, that means the size, if it is matching with a hole, you can say that the size of the flaw is at least equal to that particular hole whose echo intensity is matching with the echo intensity of that particular flaw. Okay. So, it is at least equal to that. It may be bigger than that, but we can say that it is at least equal to the size of that particular hole. Okay. So, this is one thing that you should keep in mind, that size that you estimate from this particular calibration curve is the lower limit for the actual size of the flaw. Okay. Right. So, this is how using this set of blocks you would be able to calibrate the instrument, the ultrasonic instrument, for distance and for area. So, when you calibrate the instrument for distance, the advantage that you have, let me tell you, apart from to make it free of error, that is the first objective of doing calibration. But in this case, the another advantage that you have when you calibrate the instrument for distance is that you would be able to get some idea about the depth or location of the defect if your instrument is properly calibrated. Okay. Because this time base that you have in the display so this is the initial pulse, this is the back wall, and x axis shows you the time at which the echoes appear, okay, to the probe, or the echoes come back to the probe. Okay. So, this time can be converted into distance if you know the velocity of sound wave in the material which is being tested. Okay. And most of the time it is known, because in most of the common metals, alloys and many other materials, the velocity of sound is known. So, if you provide the velocity of sound, this time can be converted into distance, because we know distance is velocity into time. Okay. But in this case, the other thing that you should remember, okay, this has to be divided by 2, because the waves are going back and forth. it is going here, hitting the reflecting interface, which could be the back wall or any other defect or flaws, and then coming back. Okay. So, this is going back and forth. So, that is why when you calculate the distance, it has to be divided by 2. Okay. So, that means once you give this V as an input to the instrument, this time base can be converted into depth or distance. And now, if your instrument is properly calibrated with respect to depth or distance, then you could see what depth a defect is appearing. So, that is where the defect is lying, which you could see directly on the display itself. Okay. So, this is the advantage that you have when your instrument is properly calibrated. Similarly, if you calibrate the instrument for the area, then as I said, you would be able to get some idea about the size of the flaw, at least the lower limit of the size. Okay. So, by doing the calibration, you are not only getting error free results, but you also get to know, or you get some idea about the location of the defect and some idea about the size also. Okay. So, ultrasonic testing in that sense provide you some quantitative information also, although it is primarily a qualitative test, but through this kind of calibration and this kind of calculations, you would be able to get some idea about the depth at which the defects are located, and also some idea about the size of the flaws. Okay. So, this is how calibration helps you. But as you could see in this case, this is primarily for a normal probe, okay, which is going perpendicular to the surface like this. But there are many scenarios in which you have to use an angle probe, you have to use an incident angle, and for that case also you need to calibrate the instrument. And as you would have realized, by using this kind of simple cylindrical block, you cannot calibrate the angle probes, because here there is no incident angle as such. So, that means when you want to use an angle probe, you need some other kind of reference block or calibration block, which would be able to calibrate the angles as well. Okay. So, that is what we are going to talk about next, as to how to calibrate angle probes and what kind of calibration block is available for calibrating the angle probes. Okay. But for today, this is all I will have. I will take that up in the next class, but for today I will stop here. Thank you for your attention.